Hi, everybody. This is Miss Wiesen, and this is the second podcast of Unit 2. And today we're going to spend some time talking about types of chemical reactions, but most importantly, we're going to touch on how to write chemical reactions, how to balance them, how to write their ionic equations, and things of that nature. So, what is a chemical reaction? It is a series of reactants showing how they form into their products. So the basic format of a chemical reaction is you will always write the reactants on the left side of the arrow. You'll then draw an arrow to indicate that chemistry has happened, and what results is what we call our products. It might actually be worth it right now if we did an example in our notes. And so I actually have a reaction here. Why don't you pause me? You can jot this down. Again, I'm going to kind of go slow on this so you can see the nuances of balancing a chemical reaction if it's been a long time for you. Okay, so the first thing I see is my reactants. I see my products. I see no coefficients. Therefore, I need to balance the reaction. What I generally do when I'm teaching this to my first year chemistry students is I kind of separate the reactants from the products. I go and start at my left side of my equation and I list out all of my elements individually. So I'm going to start from left to right. I see copper, I see chlorine, I see silver. Now I notice that there is a polyatomic ion here. It would be in your best interest and easier if you would just separate everything out, but keep your polyatomic ions together. And we know that nitrate is NO3, so I'm going to write NO3. Now, because the conservation of law and mass says what I am starting with is ultimately what I'm going to be ending with, then I would expect that the product side has the same elements as well. So I'm going to write them in the same order: copper, chlorine, silver, and nitrate. First thing I'm going to do is my initial counts. Now I'm going to go back to the left side and I'm going to do my initial counts of copper. There's only one. I see that there are two chlorines. I see that there's only one silver, and there is only one polyatomic ion of nitrate. So there's only one. Now go ahead to your right side and do your counts as well. I see that there's only one copper. In this case, there's only one chlorine. There's only one silver. And in this case, there are two nitrates. If you look at these numbers, they are not the same. That's a problem. We need to get them same. I can see that we have the same number of copper, but there is a discrepancy in chlorine. I have two on my reactant side and only one on my product side. So I can only add and change coefficients when I'm balancing equations. I cannot touch subscripts. So if I go to the right-hand side of the equation, I need to put that a 2 in front of this compound to indicate that there are two chlorine. Now, what that does is it consequently changes how many Ags or silvers we have. So I'm going to go ahead and write a 2 next to the what number that I just originally put, because now there are two. Now, what that does is it skews me off on the left side. I only have one Ag, but I could fix that by putting a 2 coefficient in front of that Ag. That 2 is distributed to the silver, so now I have 2, but now I also have 2 nitrates. And you can see that all of our numbers match and we are balanced. Very quick overview on how to balance, you guys. You need to know it. If you need more help, you should reach out to me. Thank you very much. One of the things that you're going to need to get into the habit of is putting the state of matter of that substance after you write it in the balanced chemical reaction. So S is solid, liquid, gas, and aqueous. Make a note that in balanced chemical reactions, there is no indication of the energy exchange happening, nor of the time duration that it takes for the reaction to occur. So before we begin, the first type of reaction we are going to talk about is something called a precipitation reaction. You've probably heard of something called a precipitate form. Well, precipitation reactions are a primary huge type of chemical reaction in chemistry that you need to know. And what's going to happen is when two solutions are mixed together, a solid or a precipitate is going to ultimately form. And that precipitate is actually going to be a product of the reaction. We're going to go ahead and abbreviate precipitate, PPT, if we're having to write this out for time's sake. You guys did a lab earlier this year where you used filtration or gravimetric analysis to isolate a precipitate that formed from the hard water lab. Some of you are out there are going to ask me, well, how do I know a precipitate is going to form? If you can't actually run the chemical reaction in person, how then would you know that the precipitate forms? And that's actually when you're going to want to consult your solubility rules. Now, it's my hope that this is not the first time you've seen this. What I would do is put me on pause and make yourself some flashcards. You need to know your solubility rules. Guarantee it that there's going to be multiple questions that pop up in learning checks, finals, or even the AP test in May where you need to know these rules. Anything that is soluble, in fact, does dissolve. So it is dissolvable. If it is insoluble, that is when the precipitate is going to form. So it does not dissolve. Precipitate is the thing that forms because it does not dissolve, if that makes sense. And I hope it does. In the next exercise problem that we're getting ready to do, you need to have these solubility rules right in front of you so you can pause me and go back and look at how these are used in determining whether a precipitate is going to form or not. Let's do exercise 18 and kind of apply those solubility rules. Now, it's not necessary to show the full chemical reactions here, but I'm going to because I think you need to see how to write chemical reactions and how to balance them and the fundamental things you learned in first year chemistry. Again, you need your solubility rules, and it's asking in exercise 8 to use those rules and predict what's going to happen when you have two solutions coming together. I'm going to do the first one for you. I really want you to do B and C and follow up, and in class, we'll probably do one of these in class. Okay, so let's go ahead and do exercise 8A. It's telling us that we are going to take a solution of potassium nitrate, and you know it's a solution because it says aqueous. And we're going to mix that with an aqueous solution of barium chloride. So if you know that these are your two reactants, what you would start off by doing is writing them as your reactants. Okay. Now, how do you know what products are going to form here? Well, in a reaction where you have two ionic compounds, where one substance has a metal and a nonmetal, and so does the other. So I'm going to go ahead and highlight them in color, so different colors, so you can see what's going on. I'm going to write their ions. So you would have potassium separating and breaking off. And of course, we know potassium is going to form a +1. You're going to also have nitrate. Polyatomic ions stay together. But nitrate is going to separate out into its ion, NO3 -1. Barium chloride is going to do the same thing. So barium is going to separate into its barium 2+. And then chlorine is also going to separate out into chlorine minus. Now, let me go ahead, and before we balance this equation, I'm just trying to give you the overview of how this reaction occurs. Now, as the ions start floating around in solution, oftentimes what will happen is the cation of one compound is now going to hook up with the anion of another compound. The opposite's true. Barium, the cation of one compound, is now going to hook up with the anion or the negative ion of the other compound. And so what you're going to do now is on the product side, rewrite the new combination. And so up here, back at the top, potassium is going to, which is a +1, you guys, is going to hook up with chlorine, which is a -1. Remember, to write the compound, these two charges have to balance to 0. Well, it just so happens a +1 and a -1 equals 0. So do not write the ion charges. You'll just simply write the compound with no charges because the charges are no longer there. Let's go ahead and write barium nitrate. So as a quick note, you guys, barium is a 2+, so it's going to bring 2 charges to the dance, but nitrate ion only has a -1. The charges need to balance to 0 again. So what you're going to need to do to balance this out is you're going to need to recruit, if you will, another nitrate polyatomic anion. And of course, it always is going to bring a -1 to the dance. And look at now, everybody's got a partner to the dance. I know it's a silly analogy, but it helps visualize what's actually happening here. So how do we write this formula over here on the product side? Well, you only have one barium. Remember, the metal is always written first. And then you have 2 nitrates. So you have to put nitrate in parentheses, close it off, and say 2. All right, so I'm going to go ahead and erase this bottom part here. I'm going to end up rewriting it, but I wanted to show you the rationalization on how you can visualize how two ionic aqueous solutions come together and what is happening. They're doing a little switcherooski. All right, so now what we need to do is balance the chemical reaction overall. And you can see here that right now we don't have any coefficients in front of these substances. And so let's go ahead and draw that line, separate our reactants from our products, and list out all of our individual elements. Now you're going to do an initial count. Now it is clear that these numbers are not the same on both sides, therefore the equation's not balanced. I notice my potassiums are balanced, but what I see a discrepancy in right off the bat is my nitrates. I have only 1 on my reactant side, and I need to turn that and change it to a 2. Remember, don't mess with subscripts. You can only change coefficients. So over here, I'm going to put a 2 coefficient in front of the substance that has the nitrate ion. Yes, that 2 is going to affect how many potassiums you have now, but it will also establish the correct number of nitrates. So what I'm going to do is I'm changing color, and I'm going to scratch out the original number because I no longer have 1 potassium, but now I have 2, and I no longer have 1 nitrate. I have 2. So again, we are still not balanced here. I'm going to come back up here, and I work my way from top to bottom, you guys. Usually that helps me keep balancing chemical equations organized. And because now I have 2 potassiums on my reactants, I need to change that number on my product side. I can only add coefficients. That's it. So I'm going to have to add a 2 there, distribute that 2 to the potassium. Yes, now you have 2 potassiums. But what does it do to the chlorine, you guys? It also changes the number of chlorines on that side only. And so come on down here and go ahead and scratch off the old number because you no longer have 1, but now you have 2. I'm looking and I notice that the numbers are identical on both sides of the equation, and therefore my equation is balanced. But what we've done is we've taken 2 reactants, we've determined the products. We haven't determined which one of the products is going to be soluble versus insoluble. That's when we need to look at the solubility rules now. Look at the products. Is potassium chloride going to be aqueous? Is it going to stay as ions in solution, or is it going to drop out as a solid? Or could it be that barium nitrate is the solid? That is when you need to go back up to your solubility rules. And I will give you a second here to tell me what happens. If you've come back and you've told me that potassium chloride is going to be soluble, what that means is no solid is going to form. So this substance stays aqueous in solution. How about barium nitrate? Oh my goodness, you should have looked at your solubility rules and determined that barium nitrate is also soluble. In other words, it will not form a solid. So it will also remain aqueous. Now, the first 2 solutions were also aqueous, so make sure you include that state of matter as well. Now, what you have noticed here is that no solid formed. When no solid forms, you can basically say that as the same thing as no reaction is occurring. All right. Now, I want you to try B and C, and I'm going to give you a hint. B and C will have solids forming. So I want you to use those solubility rules, write the balanced reaction, and determine which of your products forms the solid by consulting your solubility rules. Again, I really do think that we're going to need to go over one of these in class, but it's worth it for you trying initially. Now, when you write chemical reactions, you're going to do it in 3 steps. This is called the AP style, or the AP way of writing reactions, and you're going to do it in 3 steps. The first thing you're going to do is you're going to write the complete balanced equation. And that's basically just writing the reactants and products and balancing the equation. The second thing you're going to do is then you're going to separate everything out into their ions and write the complete ionic equation. And lastly, once you determine your spectator ions, which you'll see in just a second what those are, you are going to write your net ionic equation. Okay. Overall, you need to know this, that when you're doing the AP style way of writing equations, you're always going to need to conserve the charge in the net ionic equation. If that's a little confusing to you, fear not. We're going to go ahead and do example in exercise 9. So make sure you have your solubility rules out because you always need your solubility rules when you're doing precipitation reactions. Okay, so it's asking for each of the reactions below, write the number 1, complete balanced reaction. That's the first thing we're always going to do. And then from that, you're going to determine and write the complete ionic equation. You're going to determine your spectator ions and then write your net ionic equation. 1, 2, 3, bam. I'm promising you right now that almost always number the 4th FRQ in your AP test in May will include one of these types of reactions where you have to write the complete balanced reaction, the complete ionic reaction, and the net ionic reaction. Here we have, it doesn't give us any formulas. It only tells us in words. This is where you need to go back and do a review on how you are writing formulas, balancing those formulas. And then, of course, from that, we're going to write balanced reactions. Everything builds off of each other. I'm going to hold you to the fire. You need to know how to write formulas. You're going to see an example here. We're going to do A, and I am deciding right now we're going to do B in class. I think that will be a great overview as well to do B in class. Don't leave that blank. I want you to try it before you come to class because that's how you learn. You learn where your mistakes are and correct that thinking. All right, so let's do number 1. Aqueous potassium chloride is going to be added to aqueous silver nitrate to form a silver chloride precipitate plus an aqueous potassium nitrate. Ooh, they already kind of tell us what actually forms our solid. So it appears that we don't need to be, it appears that we do not need to look at our solubility rules because it tells us what is precipitating out here in the problem. That's nice of them, but half the time they won't do that. Okay, so let's go ahead and write the first thing we're going to do is write the balanced reaction. All right, aqueous potassium chloride. Potassium's a +1. Chlorine's a -1. The charges of the two need to balance to 0. Well, that just happens to be convenient because we only need one of each to balance the charges out to 0. Okay, and if it's aqueous, of course, you're just going to write an AQ next to it. And this is added to aqueous silver nitrate. When it's added to, you indicate with a plus sign, and, or added to, aqueous silver nitrate. Silver is Ag. Silver is a transition metal, and sometimes we don't know the charges of transition metals. However, we always know that silver is going to form a +1. It is an exception. We do know silver will always be a +1. Nitrate is NO3, and the charge on a nitrate is a -1. Go to the dance, balance your charges to 0. A +1 and a -1 already equal 0. Sweet. So this thing is already balanced to 0, so we just need to write them together. Do not write the charges when you're done balancing the formula. All right, and that is going to, so there we go. Now it's going to form. So every time you see the word form or a reaction occurs or will result in, you're going to draw that arrow. And it's going to form silver chloride. And remember, silver is Ag. Chloride is Cl -1. Balance the charges to 0. Well, there's only one of each. So the formula is AgCl. And then that is actually going to be our precipitate. So that's when you put an S. That's when the solid forms. Oh, I apologize. Let's go back here and put aqueous next to the other reactant. Right? It's a bad habit. Sometimes I forget. All right, and then it's going to say you also form aqueous potassium nitrate. Potassium's a +1, nitrate is a -1, so you only need one of each. Therefore, you have KNO3, and it is aqueous, so you write AQ. All right, you're not done. You just wrote the complete reaction, but you have not balanced it. So again, I always draw my lines, separate my substances, but this one, do you really need to do that? Some of these reactions are going to be so simple, you don't need to go through that whole process. You can see it in your head. Really quick, I'm just going to take you how I think through. I think I see one potassium over here and one potassium. Okay, that's sweet. We're good. I see one chlorine. I see one silver over here and one silver over there. And I see one nitrate here and one nitrate there. It appears that there are the same number of each element on both sides of the equation, so it is actually balanced. Now, you don't have to write the one coefficients in front. You don't need to. It's implied that if there is no number there, that it's already a 1. So make sure you understand that, okay? All right, so here is your complete balanced reaction. This is the first part in the 3-part series. The second thing you are going to do now is you are going to take the substances that can break apart into its ions, and you're going to write what we call the complete ionic equation. All right, so think about this. What substances do you think are going to break into their ions? Well, we know it's not going to be the solid. The solid is bound together as a precipitate solid sitting at the bottom of the reaction vessel. That is not going to break out into its ions. But what will break out into its ions is anything aqueous, okay? It's already actually floating around as ions in solution. So when you go to write the complete ionic equation, what you're going to do is you need to indicate charge and how many. And so that's when the coefficient's going to come into play. From the balanced chemical equation, your coefficient's going to tell you how many of those ions are floating around in solution. So let's begin. I'm going to have 1 potassium. Don't forget the charge. I'm going to have 1 chlorine, -1. Don't forget the charge. Now let's skip on over to silver nitrate. That 1 coefficient tells me I have 1 silver +1. It also tells me I only have 1 nitrate. Don't forget your charges. Now I know that the silver chloride is not going to break apart into its ions because it's a solid. However, the substance that remains on the product side, this potassium nitrate, since it's aqueous, it will also break apart into its ions. And don't forget to indicate how many there are. Again, the coefficients and subscripts will tell you that. Okay, so what I want you to do is identify the same ions on both sides of the reaction. Okay, so I see here that I have a potassium ion floating around in solution, and I have another one over here. What this means is that potassium is not going to take part in this reaction. It is a spectator ion. It's just hanging around freeloading. Okay, it doesn't have any overall effect in the reaction. Now go ahead and take a chlorine ion. Is that going to be a part of the reaction? Yes, it actually is a part of forming the solid. So chlorine over here is not a spectator ion. And the same thing with silver. Silver is an ion over here, but it's bound to chlorine to form the solid on the product side. Lastly, look at nitrate. Nitrate and the nitrate over here, these are just ions floating around in solution. They don't have anything to do with the solid that formed or the chemistry that happened. And so what that means is that they are also spectator ions. They're freeloaders, as I like to say. So then the third thing you're going to do, and this is the third equation, is you're going to write the net ionic equation. So you're going to write everything that remains. Do not include the spectator ions. All right. And so what you have just learned here is, again, let's recap. You have learned to write a complete balanced reaction. You then learned how to separate that out into its ions, and you're only doing that for aqueous solutions. And then the last thing you are going to do is, after you cancel the freeloaders, you're going to just write what remains, hence net ionic equation. Okay, we'll do exercise 9, part B in class. You need to try it. I'm sorry about putting the answers and the solutions right smack dab in the middle of the box there. We're going to do exercise 10 in class as well. And then before we end this podcast, we're going to do exercise 11. Now, this is a limiting reactant opportunity, and we need to do these as many as we can because they love to ask these types of questions. And so what we got here is we have an aqueous solution of sodium sulfate. And it looks like we also have, it's being mixed with lead nitrate. And both of those are aqueous. So I wrote those down as both of my reactants because we're going to mix those two together. And it says when they are mixed, we have a precipitate. And it looks like it's lead sulfate. And I would need to put an S there, you guys. That's what it means when it says precipitate. It's asking us to calculate the mass of the precipitate, the lead sulfate. So I'm just going to kind of highlight what it's asking for underneath so you can kind of see where we're going here. Now it's saying how much of this solid are we going to form if we had 1.25 liters of a 0.5 molarity lead sulfate solution and 2 liters of a 0.025 molarity sodium sulfate solution. Okay, so don't try to visualize this problem. And if you need to, write things out. As you can see, what I've done here is I wrote out the equation and I put the information associated with each species below it so it can kind of visualize what's going on here. Now, some of you might be asking, isn't there going to be another product that forms over here? And the problem didn't mention it, but we should just mention it right now. Remember, when you have two ionic aqueous solutions, they're going to do the little switcherooski, as I like to say. We can already see how this lead hooked up with this sulfate. And that's actually the solid that formed over here, you guys. The other product that's going to form is when we have sodium and nitrate coming together. So what I want to do is just finish up writing the products of this reaction, even though they did not give them to us in the problem. And so over here in my thinking bubble, I know that sodium is going to form a +1. It's going to hook up with nitrate. NO3 is a -1. 1 plus 1 minus, these equal 0. Now I can write the formula. So let me go ahead and write it in its appropriate spot. So NaNO3, there's only one of each. And of course, that's aqueous. I assume it's aqueous because we already had the solid lead sulfate form. Alrighty, so one of the things that we need to do, you guys, always get into the habit to make sure that this is balanced. I'm going to do this kind of visually in my head instead of drawing the line and separating things out, just because that takes a long time. Again, my method is pretty straightforward. I notice that on my left side, I have 2 sodiums, and I go over here to my right side and notice that there's only 1. Of course, I can only change the number of elements by coefficient. So I'd have to put a 2 over here. Now, yes, that 2 does now give me 2 sodium like I need, but it also changes the number of nitrates that I have, which I have 2. And that ends up working out for us because if you go back to the left side of the equation, I have 2 nitrates. I have 2 nitrates. So I'm looking at lead. Lead seems to be balanced. Everything looks to be balanced right now, you guys. So the coefficients of our reaction are 1, 1, 1, 2, respectively. So we haven't even started yet, but that's okay. It's basically saying, all right, if I start off with a certain volume and concentration of each of these aqueous solutions, what is the most amount of the product that can form? So we call this a limiting reactant problem. In other words, which one of our reactants, which one, you guys, is going to limit how much of this stuff we're producing? That's what we need to determine, because as soon as we determine which of the reactants is limiting the product formation, that's going to be our answer. So I'm just going to go ahead and work the problem for you. Let's start off and see which one, see how much product forms from the first reactant. And so one of the things I have to recognize is the information that they gave me in this problem is going to allow me to determine how many grams of the product is going to form. Now, a side note here, you guys, when you see molarity, I want you to know that's moles per liter. Okay, so doesn't it make sense then? Actually, I'll write that over here to the side. Now, look at what they also gave us. They gave us volume of this aqueous solution we're mixing with the other substance. We're mixing in 2 liters. And wouldn't it make sense then, just follow my logic here, I've got 2 liters of this sodium sulfate solution. I'm going to go ahead and do some stoichiometry, guys, and my end goal is to figure out, again, how many grams of the product are going to form. So check this out. If I know I have 2 liters of this particular substance, and I know the molarity, which I know that liters is in my denominator, I know that for every 1 liter of sodium sulfate is going to be 0.0250 moles of sodium sulfate. Yep, that's where I put molarity. Liters cancel. I'm in moles. I need to go to grams of the product. So I definitely am not done yet. Well, what if I now told you that the purpose of balancing the equation was to do a mole-to-mole ratio? Go back, and I see that for every 1 mole of sodium sulfate, is going to be equal to 1 mole of lead sulfate. So this is the conversion factor right here, where I actually make the jump from the reactant to the product. So I make sure my units align. So down here goes 1 mole of Na2SO4, and that is to 1 mole of the product we're trying to figure out how much formed. Okay, go ahead and cancel moles of sodium sulfate. Now you are in moles of lead sulfate. How do you go to grams? That's right, molar mass. So you need to find the molar mass of lead sulfate. I already did that, you guys, and I know that down in my denominator here, I need to put 1 mole of lead sulfate. And for every 1 mole, I think hopefully you got the same thing. You should double check me, 303.26 grams of lead sulfate. Whew, that's called stoichiometry, you guys. Moles of lead sulfate cancel out. I'm in grams. I'm going to go ahead and plug this in onto my calculator, and when I do, I get 15.2 grams of the product forming. Okay, so that is how many grams of the product forms when it comes to terms of the sodium sulfate reactant. Now we have to do the same thing, but for the other reactant of lead nitrate. Notice that lead nitrate, you know that you have 1.25 liters of this lead nitrate. And you also were given molarity. So this is our opportunity to make a conversion. So the molarity was given to us. It was 0.5. And we know that for what that means is for every 1 liter of lead nitrate is going to be 0.5 moles of lead nitrate. And we use mole-to-mole ratios to make the jump from the reactant to the product that we're interested in. And again, it's a 1-to-1 ratio, as you can see from the coefficients from the balanced chemical equation. And so down here, you want to make sure your units align, let the units guide you, as to 1 mole of lead sulfate. Cancel your moles of lead nitrate. Now, last thing, how do we go from moles of the product to grams? Yes, you're going to use molar mass again. So we already determined what it was in the first step. It was 303.26 grams. Sorry about my handwriting, you guys. Cross-cancel your like units. I'm in grams. I'm done. Well, I need to calculate, but I'm done setting it up. When I did the calculation here, you guys, I got a huge number. 189.5 grams of lead sulfate would be formed if we're taking into consideration the lead nitrate reactant. Again, which number is less here? Which number has the smallest quantity of the product? Bingo. This one, 15.2 grams, is less than 189.5. So if I were to ask you which reactant is the limiting reactant, go take a gander at what reactant caused that smaller quantity. So therefore, Na2SO4 is your limiting reactant, and 15.2 grams of the solid is going to form. Okay, you guys, that's going to end it for this presentation. Thank you so much for watching.